The Fundamental Theorem of Algebra is what we're going to talk about in this video. Okay, now what exactly the Fundamental Theorem of Algebra is about and why the topic that it's about is given such a prominent name as the fundamental theorem of the entire subject. I think for the Fundamental Theorem of Algebra, it's a little bit harder to comprehend why this is labeled as the central theorem of all of algebra compared to, for example, like the Fundamental Theorem of Calculus. I think on the surface, it's a little more intuitive why, okay, yeah, this is like the central theorem of the entire subject. Okay, so just to give you a preview before we get into the specifics, what the Fundamental Theorem of Algebra is all about is, so right now we're going through the first part of Chapter 3, which is on, Chapter 3 is on polynomial and rational functions, but the first half is we're focusing on polynomial functions. Okay, and in the last few videos, we've been talking about and working example problems on the remainder and factor theorems and the rational zero theorem. And as you know, what these theorems are useful for is that they give us significantly more versatility for factoring polynomials than the skills we learned in pre-algebra for factoring polynomials. Significantly more versatility. Okay, but as you know, it's not just factoring polynomials. With those same skills, you could also find the zeros of a polynomial. Okay, and so all that the fundamental theorem is going to tell us is exactly how many zeros or roots any nth degree polynomial is going to have. So if you have any polynomial of degree n, so a sub n, x to the n, and then all the way down to the constant term, exactly how many roots is this polynomial going to have? Now, as far as the usefulness of knowing this for factoring a polynomial or finding the zeros of a polynomial, you could definitely argue that the factor theorem or the rational zero theorem is more useful. However, I think you would agree that a statement like this, that's telling you the number of roots that an nth degree polynomial is going to have, and it's going to be, the answer is n roots, that's kind of a central, fundamental, overarching statement for this entire topic of factoring polynomials and finding roots of polynomials. Right, if you're going to label one of these theorems as the fundamental theorem, if you're going to choose between the remainder theorem, the factor theorem, the rational zero theorem, etc., and label it as the fundamental theorem, even though it's probably not as useful as like the rational zero theorem, this seems like more of a headline statement. If you have any polynomial of degree n, then it's going to have exactly n zeros or n factors. Okay, so again, I'm not a mathematician, but this is my opinion on why this is labeled as the fundamental theorem. Now you might say, well, okay, I get that, but what's so special about this topic? Yeah, so this is the most fundamental theorem related to this topic here that we're studying of factoring polynomials and finding zeros of polynomials. So why isn't it the fundamental theorem of factoring polynomials? Well, again, I'm not a mathematician or a math historian, but one way you could look at it is, you know, it would seem that of all of the different expressions that or types of math expressions we learned in pre-algebra and that we've been solving equations for and we're analyzing functions and relations for, rational exponents, so roots. We're going to analyze logarithms, exponentials, absolute values, rational expressions. Probably the most fundamental is the polynomial, right? In all of algebra, if you're going to have a headline symbol for algebra, you'd put a polynomial, a power term, right? You could argue that the polynomial is everything is centered around the polynomial, you would think. Okay, so now what kinds of things do we learn in algebra? Well, we learn about solving equations, we learn about functions. So when you think about a function, you think about its graph. We learn about factoring. Well, this topic that we're learning right now, that the fundamental theorem is centered about, it's related to factoring polynomials. It gives you an extreme amount of versatility for factoring polynomials. But when you factor polynomials, you can find the zeros of a polynomial, which means you can graph the x-intercepts. Not only find the zeros, but find the multiplicity of the zeros. So as you know, once you can get the zeros of a polynomial and their multiplicities, other than maybe you just need the y-intercept and you can graph the shape. So the fundamental theorem is central to the graphs of polynomials, factoring polynomials, solving polynomial equations. How do you solve a polynomial equation? You have to factor the polynomial. Okay, so that's why, in my opinion, this is labeled as the fundamental theorem of this entire subject. Okay, so before we get into this, it's important to note that, so most of the time when we're dealing with a polynomial, if we're factoring it, finding the zeros, etc., we're strictly looking at, we're thinking about it like, so if we've got a polynomial, let's say 5x cubed minus 2x squared plus 7x minus 3. Okay, maybe we want to factor this, plot this, find the zeros, etc. Or maybe we're doing like a mod. This is modeling something in real life. There's an equation for something, you know, a cost of something or whatever. Typically, the way we're thinking about it is the polynomial, the coefficients can be any real number, and the acceptable inputs for the x values is any real number from negative infinity to infinity. Okay, and then with that, when we actually solve for the zeros, we still might find some imaginary zeros, and we go ahead and sometimes just list those imaginary zeros as well, in addition to the real zeros. Okay, that's the most common way we approach dealing with polynomials. However, for the fundamental theorem of algebra, we want to look at the definition of the polynomial from the most general viewpoint. Okay, and so the most general viewpoint is we've got, so you got a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to the constant term. Okay, now instead of these coefficients being restricted to only real numbers, for the most general case, we allow real or imaginary numbers for the coefficients. And similarly, instead of just allowing for real number inputs, for x, we allow for real or imaginary numbers, so any input. This is the kind of polynomial we're thinking about in this section, talking about the fundamental theorem of algebra. Okay, so it says, in the previous examples, we see that the zeros of a polynomial may be real numbers, either rational or irrational, or non-real numbers, such as 2 plus 3i or 5i. Yeah, that's what we saw. We either have irrational or rational zeros with the corresponding rational or irrational factors, or there's complex zeros with complex factors. Now it says, in any case, the zeros are all complex numbers. So what this sentence is a little confusing. What they're saying here is, for what we're about to talk about, thinking about this most general polynomial, even the real zeros in real roots, we can think about those as complex numbers as well. So if we got a zero we found x is equal to 5 was a 0. So that the root of that would be x minus 5. Well, this is technically a complex number, right? All numbers are complex numbers. This just has it's 5 plus 0 I, right? So they want us to look at this from the perspective of really all numbers are complex numbers. The entire complex plane, when you look at for all numbers that exist, all the existing numbers in mathematics, you can plot in a plane. And just because if you're on the real number axis, you're still in the complex plane. So that's how they're wanting us, the perspective they're wanting us to get into here. All right. So it says, to find the zeros of a polynomial, it is important to know how many zeros to expect. This is answered by the following 3 theorems. So yeah, we're about to look at a group of theorems. The first is called the Fundamental Theorem of Algebra because it is so basic to the foundation of algebra. Okay, so here's the Fundamental Theorem of Algebra. Now, this is a little confusing because I've watched a lot of videos that. So let's read this. The fundamental theorem of algebra. If f of x is a polynomial of degree n is greater than or equal to 1 with complex coefficients, which this includes real numbers, right? It's just any kind of any number, then f of x has at least one complex 0. And this is kind of confusing too, because it's like, are they talking about it's an imaginary number? No, this includes anything. This includes real numbers. It's any 0 because they're including a real number as complex for these theorems here. So it's just, in general, it's saying, if you look at it completely general, that the most general polynomial with n is greater than or equal to 1, the degree is greater than or equal to 1, then it's going to have at least one 0. Complex, real, whatever. As long as you're allowing the most general polynomial with complex coefficients and you allow complex numbers to be input for x, then it's going to have at least one 0, complex, imagine, or real, whatever. Now, what's confusing, though, is that, well, this isn't what exactly what I stated the fundamental theorem was at the beginning of this video. It doesn't say that it's going to have n zeros in the degree of the polynomial. It says at least one 0. And it actually isn't till the linear factorization theorem that this is really what ends up stating that a polynomial of degree n is going to have n zeros. Okay, again, but I've watched a bunch of videos. I think I saw like a Khan Academy video where they state what they're calling the what's based on the linear factorization theorem. They state that as the fundamental theorem of algebra, saying, an n degree polynomial has n zeros. So, I'm not a math historian. You're welcome to do your own research and you could just go look at what is shown in this college algebra textbook here and decide for yourself. But, okay, so that's what they state here, that a polynomial, as long as its degree is greater than or equal to 1, is going to have any polynomial is going to have at least one 0. Okay, so it says the fundamental theorem of algebra, first proved by German mathematician Carl Friedrich Gauss, guarantees that every polynomial of degree n is greater than or equal to 1 has at least one 0. Now, suppose that f of x is a polynomial of degree greater than or equal to 1 with complex coefficients, the most general polynomial. The fundamental theorem of algebra guarantees the existence of at least one complex 0. Let's call this C1. Again, this could be a real 0 as well. It's just any number, real or imaginary. By the factor theorem, we have, so by the factor theorem, there's no remainder, right? We learned the factor theorem in the previous section. There's not going to be a remainder, and you're going to have, and this is going to be the quotient. This is the, well, no, not the quotient. This is the divisor. You divide the polynomial by the divisor, and since it's a factor, it doesn't have a remainder. So there's the divisor times the quotient, where the quotient is a polynomial of degree n minus 1. Yeah, the quotient is always 1. Well, it's not always 1 degree less. It's you take the degree of the polynomial minus the degree of the divisor, and that's going to be the degree of the quotient. But since the degree, we're saying here that the divisor has degree 1, so we know that the quotient is going to be degree n minus 1. Okay, so if q1 of x is of degree 1 or more, then the fundamental theorem of algebra guarantees that q1 of x must have at least one complex 0. Call this C2. Okay, so if they're saying after you've taken out this, what they've done here is we have a polynomial. It has a complex 0, C1, or just a 0. You write that as a factor, and you divide it, and then you factor it out. And you're left with the quote. This is what you're left with when you factor it out. If this still has a degree of greater than or equal to 1, it's going to have 100% have it, according to what they're calling the fundamental theorem, at least one 0. Call this C2. You factor that out, and there's Q2. And then same thing. You get another quotient. If that has degree n minus 2 from the n of the original polynomial, if that has degree greater than or equal to 1, that has 100% has a factor or a 0. So you can just do this over and over and over again until you get to the quotient having degree less than 1, which means it's just a constant. And it says, so we continue with this reasoning until the quotient polynomial is a constant and it's going to be equal to the leading coefficient of the original polynomial. That's interesting too. The actual, once you get to the constant, it's going to be equal to the leading coefficient of the original polynomial. And so you can see how they developed all this with what they're calling the fundamental theorem of algebra, and now they state another theorem, which is called the linear factorization theorem. You've got a polynomial here with n is greater than or equal to 1, completely general, allowing for complex coefficients, all that. Then, okay, they've got this constant out front with a bunch of linear factors here. So a linear factor can be anything, any ax plus b. So here they're showing the a is equal to 1, but a linear factor is any ax plus b. And it could be squared or whatever. Just there's no ax squared or anything like that. It's ax plus b, with a could be equal to 1, b could be equal to 0, whatever. And you could have it could be any multiplicity. Okay, and it's saying that the c's are all complex numbers. They could be real numbers though. They're just, again, we're treating every number as a complex number for these theorems. Okay, now let's see. Note the complex numbers are not necessarily unique. Yeah, so they're saying what that means is you could have like an x minus 2 here, and then you find an x minus 2. And then you could combine that to get x minus 2 squared. So they don't state it explicitly here. I'm not sure why they didn't state it explicitly, but yeah, based on the fundamental theorem of algebra, they could create this theorem which says you could take any polynomial, no matter what, and you can write it this way as a product of n linear factors with a constant out front. N linear factors, and you count the multiplicities though as well. So like if you had x minus 2 twice, you count that's counted twice when you're counting up to n. Okay, and so this is what I thought, all of this combined, I thought was the entire fundamental theorem of algebra, but according to this textbook, apparently not. So, but anyway, okay. So, oh, yeah, and I want to point this out too, that, so, okay, if we come back to the beginning of this section, so, okay, the section started off, we were given this polynomial here, which this was, more of an example of a polynomial that doesn't have complex coefficients, more of a typical polynomial we would deal with. And, we couldn't factor this by normal means, and so it was demonstrated how we could use the factor theorem and the rational zero theorem to factor it like this. Okay, but so here's an example of they've factored this into 1, 2, 3, 4, 5, 6 linear factors. Okay, and that makes sense based on the fundamental theorem. You could factor any polynomial into 6 linear factors. Now we're gonna talk about, when we get to partial fraction decomposition, it states that, so when you do partial fraction decomposition, what you're doing is you're breaking down a rational function, so it's a ratio of polynomials, and you're breaking it down into a sum of simpler polynomials. And the idea is you need to do this, you need to factor the polynomial in the denominator, and it says to strictly linear and quadratic factors. Okay, linear and quadratic factors. So, and what we'll see is that's what we do partial fraction decomposition with. As long as we've got some product in the denominator of linear and quadratic factors of any multiplicity, then we can do the partial fraction decomposition. Okay, and so it's powerful that any polynomial, no matter what it is, ultimately can be factored into a product of linear and quadratic factors. Now, what I want to point out here is that you might say, well, why not just all linear factors? We can't factor any polynomial down into all linear factors. Isn't that what the fundamental theorem says? Yes. However, if you don't include as part of those factors the non-real factors, then you have to restate it to where the farthest you could go is linear and quadratic factors. And to see what I mean by that is that, like, okay, here, yeah, these are all linear, but if we didn't allow for the inclusion of anything non-real, well then, okay, we've got x minus let's see, that would be minus 2 minus 3i, and then x minus 2 plus 3i. Okay, so yeah, let's multiply these together. So x squared minus 2x plus 3xi minus 2x plus 4 minus 6i minus 3xi plus 6i minus 9i squared. Okay, so we've got minus 3xi plus 3xi goes away, minus 6i plus 6i goes away, minus 9i squared becomes plus 9, so we're left with x squared minus 4x plus 4 plus 9 is 13. And so there's, what you do is you just leave the quadratic factor as is. You leave the complex numbers, imaginary numbers, inside the quadratic instead of factoring it further. And so what you end up left with is a product of all real linear and quadratic factors. And you might say, well, didn't we get lucky here that, you know, we could have been left with it when we did this multiplication, we could have been left with we got lucky that the 3xi subtracted out and the 2 6i subtracted out. What if those didn't subtract out? Well, that won't ever be an issue, and let's see why. We'll see in an upcoming theorem why that's not an issue. Okay, the linear factorization theorem tells us that a polynomial of degree n is greater than or equal to 1 with complex coefficients has exactly n linear factors of the form x minus c, where some of the factors may be repeated. The value of c in each factor is a zero of the function. So the function must also have n zeros, provided that the zeros are counted according to their multiplicities. Yeah, n zeros and n factors. It's one and the same thing. So the number of zeros of a polynomial. If f of x is a polynomial of degree n is greater than or equal to 1 with complex coefficients, then f of x has exactly n complex zeros, provided that each zero is counted by its multiplicity. Okay, and so yeah, if we come back here, what you can note is that if you're not including complex zeros, then this isn't a zero of the polynomial then, right? This is going to show, if you plotted this polynomial, it's going to have this x-intercept, it'll be 1 will be an x-intercept, minus 7/2, root 3, minus root 3, and that will be the only x-intercepts. Okay, so from that perspective, it seems to only have 4 zeros, but we know the other 2 zeros are complex or imaginary. Okay, so here's, kind of a restatement of what's supposed to be the fundamental theorem. What I always thought was, yeah, if you a completely general polynomial that allows for complex coefficients, which that also includes a polynomial with all real coefficients, because that's just a special case. That's still you're not restricting the potential for complex coefficients. Then the f of x has exactly n complex zeros, provided that each zero is counted by its multiplicity. Yeah, so you count the multiplicity. Okay, now it says, consider the polynomial from example 4. We did this example here, and we found there was 2 irrational zeros and 2 complex zeros. It says, notice that the polynomial has, that's another, so I multiplied to create that quadratic. If we come back, so you might wonder, well, we got lucky that the 6i's subtracted out and the 3xi subtracted out, but what if we only had one complex zero or complex root? Well, then there's nothing to multiply it with. So how do you, what do you do there? Well, it says, notice that the polynomial has real coefficients. Furthermore, the zeros, so yeah, it has real coefficients. Furthermore, the zeros I and minus I appear as a pair. This is not a coincidence. For a polynomial with real coefficients, if a plus bi is a 0, then a minus bi is a 0. Okay, so yeah, that's actually, I forgot to mention, it's only the case that you can factor any polynomial to strictly linear and quadratic factors all with real coefficients, if the original polynomial only has real coefficients. So what they're saying is for a polynomial with real coefficients, all real coefficients, then any imaginary root or zero is going to occur in these conjugate pairs, always. Now, if the polynomial has complex coefficients, then this rule doesn't necessarily apply. You might get a complex zero that's alone. Okay, so with a polynomial with real coefficients, if it does have imaginary zeros or imaginary roots, they're going to occur in a pair like this. Okay, that's the conjugate zeros theorem. Any imaginary zeros of a polynomial with real coefficients are going to occur in conjugate pairs, always. And so that's why if you multiply these conjugate pairs together, you're going to get a quadratic with all real coefficients. Okay, so in the next video, we're going to work a bunch of example problems just like shown here. So I'm not going to go through these here. But so given f of x is equal to this polynomial, and it gives us one of the zeros, it's an imaginary zero, complex zero, then find the remaining zeros. Well, we know one of the zeros is going to be, one of the other zeros is going to be 3 plus 4i. So that gets us to, we only have 2 left to find, and we're just going to use the rational zero theorem, the factor theorem, just same process as we had done before. But what you can think about, though, is what we're going to actually do first is what's going to be really helpful is we know how to apply synthetic division with these 2 roots. So we can actually use synthetic division to take out these roots and turn this into a quadratic. And so then we don't even need to, we can just use the quadratic formula. Okay. Here, building a polynomial with specified conditions, find a third-degree polynomial with integer coefficients and with the zeros. So, okay. Yeah, well, you can, when you want to build a polynomial based on the, and you're given the zeros, well, you write it out in factored form with those zeros. So you could write out, so this is, let's see, x minus 2/3. So that's 3x minus 2, right? If you solve for x, you get 2/3. If you set this equal to 0 and solve for x, you get 2/3. And then one of the zeros is going to be 4 plus 2i, but we know one of the other zeros must be 4 minus 2i. Well, no, we would write it like, so 3x minus 2, x minus 4 minus 2i, and then x minus 4 plus 2i. And then you multiply all that out, and you're going to get, that's what they do here. They put a out front because you can put any constant out front that you want. They multiply all this out, and they get, there it is. They choose a is equal to 3. And then here, find a polynomial of lowest degree with zeros of, yeah, we're going to work a bunch of examples like this.